Guys, welcome back to States of Matter. So in the last video we discussed about solids, liquids and gases, their few properties, their compressibility, their fluidity. In this video we'll be discussing some physical processes and the conversion from solid to liquid and liquid to gas, these things, and their kinetic molecular theory. So this is a table I have made. So all the processes are labeled. So from solid to liquid, it's actually melting. From liquid to gas, it's either evaporation or boiling. From solid to gas, it's sublimation. Now all these processes that I've mentioned, evaporation, boiling, melting and sublimation, all these are endothermic processes. As you can see, I've labeled here all the processes, all the arrows that are pointing towards right are endothermic processes. Now why is it so? It's because bonds need to be broken, the intermolecular forces need to be overcome, and for that you need energy. What is endothermic process? In which energy is required. So therefore all these are endothermic. From gas to liquid and liquid to solid, and from gas to solid, all these processes are exothermic because bonds are being formed. Which bonds? Intermolecular force of attraction. From gas to liquid, it's condensation. From liquid to solid, it's freezing. And from gas to solid, it's solidification. Alright, now there are four processes I'll be discussing in greater detail: melting, sublimation, boiling and evaporation, because we ask you questions about these. So here's melting. So it's the conversion from solid to liquid. Alright, and we sometimes ask you the definition of melting point. So melting point, it is the fixed temperature at which a pure substance melts. Alright, this is the definition of melting point. I would really much like you to note few points. First of all, you need to mention it's fixed. Second of all, pure substance. I'll tell you why in the later part of this chapter. Alright, so we ask you kinetic molecular theory. So kinetic molecular theory. First of all, we supply heat. So as heat is supplied to a solid, its particles gain energy. And start to vibrate more frequently. Now this word frequently is important because frequently shows more amount of vibrations per unit time. You cannot say vigorous, but you should say frequently because it's a better word and you'll find it in your marking schemes as well. So more frequently, and a time comes when this increased vibration overcomes the intermolecular force of attraction, overcomes the intermolecular force of attraction, and solid melts. Now there are a few things that carry immense importance as well as marks. So first of all, you need to mention that particles gain energy, and will give you 1 mark. Start to vibrate more frequently, this will give you the 2nd mark. Increased vibration overcomes the intermolecular forces, this will give you the 3rd mark. Alright, this is the kinetic molecular theory of melting. Alright, now we'll move on to boiling. So yeah, boiling. It is the conversion from liquid to gas. So just let's just get on to the kinetic molecular theory of boiling. So what you need to mention is that as heat is supplied to a liquid, its particle gain energy and start to vibrate, rotate, and translate more frequently, or you can say more in same per unit time. More frequently, a time comes when this frequent vibration frequent sorry time comes when this increased random motion, this is a better word, overcomes the intermolecular force of attraction. I'm writing IMFA to shorten it up, but again I'm reminding you, you cannot write IMFA in your exams. You have to write intermolecular forces of attraction. And liquid boils. Alright, so again the things that carry marks are its particles gain energy, this will give you 1 mark. Start to vibrate, rotate, translate more frequently, the second mark. Increased random motion, overcomes intermolecular force attraction, third mark. Important point you need to know. Alright, so first of all I want to clear few concepts. For example, this is a container, this is the liquid level, so I provide heat. I want you to understand what boiling is. So the water here starts to actually turn from liquid to gas. This becomes trapped in a bubble. Alright, now this bubble actually tries to reach the top and it applies a pressure on the surface of water. Now that pressure is being countered by atmospheric pressure. Alright, now when this bubble leaves the surface of the liquid, we'll say boiling has occurred. That is actually what boiling is, the ability of this bubble to leave this water. But what happens is that atmospheric pressure counters it. So the bubble applies a pressure known as vapor pressure, and the atmospheric pressure counters it, and at the boiling point the atmospheric pressure becomes equal to the vapor pressure. Actually, vapor pressure equalizes atmospheric pressure and this bubble escapes. You will not be ever asked about this in the exams, at least to my knowledge, but I need to clear a few things up because I want to explain something in the impurities part of this chapter and that often remain unclear. So first of all, vapor pressure. What is vapor pressure? Pressure applied by vapors. Pressure applied by vapor. Alright, and what is at another point you want to note is that at the boiling point, atmospheric pressure represented by P at equalizes vapor pressure. Alright, great. Next we'll do evaporation. Okay, so let's start with boiling. Alright, so evaporation. So boiling was the conversion from liquid to gas. Evaporation is also the conversion from liquid to gas, but what's so different about evaporation? Evaporation is a surface process. So as I told you, so this is a container, it contains water. So what happens is that particles at the surface, they're exposed to heat. When they're exposed to heat, they gain energy, and from the surface, are you noticing it's all surface? So this water molecule here tries to escape. Alright, this water molecule tries to escape. Now it will escape when it gains enough energy to overcome the intermolecular force of attraction. So that is what evaporation is. So it's a surface process. Or are you noticing everything is happening at the surface? So what is the kinetic molecular theory behind it? So kinetic molecular theory. So what you write is high energy particles from surface of liquid escape by overcoming the intermolecular force of attraction. Alright, so this is the kinetic molecular theory of evaporation. And are you noticing that when this high energy particle leaves, or let's say few high energy particles leave, the remaining particles will be at lower energy. They'll be at lower energy. Now, what does that mean actually? That means that the overall internal energy of the substance decreases. What is internal energy basically? Internal energy is the sum of energies of the molecules in a substance. So it decreases. Now what happens because of decrease in internal energy? What happens is that the overall energy of the substance decreases. And what I can say, what is the visible effect? It will be that the temperature of the substance decreases. So this phenomena is referred to as cooling effect. So evaporation causes cooling effect. So evaporation causes cooling effect. Alright. One more point. It occurs at all temperatures. Except 0 Kelvin. Moreover, there is usually no bubble formation. Right? And it is dependent on the surface area. For example, if there is a pan of this size and other pan of this size, and let's say this is A and this is B, and they have the same depth of water in B will evaporate faster because it has more surface area. Alright, now these points can also help you to compare boiling and evaporation. I hope you can do that. Now let's start with sublimation. So sublimation again is the conversion from solid to gas directly. It's from solid to gas. There are a few sublime solids that you need to know when it comes to your syllabus. Sublime solids. First is dry ice. Dry ice is also known as CO2, and you need to memorize its melting point or boiling point. One more important thing is that for all sublime solids, the melting point of the solid will be equal to the boiling point. Why? Because there you can say the melting and boiling are occurring simultaneously. So for a sublime solid, I'll write it here, melting point is equal to boiling point. And you need to know the melting point of dry ice, that is minus 78 degrees Celsius. Okay, now next is dry naphthalene, or you can say mothballs. Naphthalene, mothballs that are often found in washrooms, so mothballs. Third one is iodine, I2, it is a group 7 member. Fourth one is astatine, or AT2, is also a group 7 member. And finally, the most important one, you need to highlight this, ammonium salts. All ammonium salts will be sublime. All ammonium salts, I mean all of them are sublime. There are a few properties of ammonium salts that, if you remember, will be very beneficial. So first of all, I'll write these here, properties of ammonium salts. So first of all, they are sublime. Alright. Second, most of them are acidic, because ammonium ion is acidic. And I'll be sharing other properties that come in our syllabus with time, from time to time. Alright. Moreover, and there's one more property, they're usually white solids. If there is a color change in ammonium salts, I'll mention it. So these are the three properties that you should know right now. You should revise them so much that they become second nature to your memory. So ammonium salts are done, sublimation is done. Now I'll do heating and cooling curves right now. So here we go, this is the heating curve. So we'll just assume that we are taking ice at minus 10 degrees Celsius and we start to heat it. So ice is being heated and heated till it reaches the temperature of 0 degrees Celsius. At 0 degrees Celsius, it starts to melt, and when melting is being done, the temperature remains constant. Why? So I'll be writing the reason here. During state change, temperature remains constant. Why? Because energy being supplied, or heat being supplied, is being used up to overcome the intermolecular force of attraction. Intermolecular forces of attraction. Right? You see? So bonds are being broken, and when that is being done, energy is required, and all the energy I'm supplying to the liquid or to the solid, it's being used up. So the temperature remains constant. Same here during boiling. So first we ask you that what are the states present from minus 10 to 0? It's solid. From 0 at 0 degrees Celsius, both solid and liquid. From 0 to 100, only liquid. From at 100 degrees Celsius, both liquid and gas. And after 100 degrees Celsius, it's all gas. Alright. The cooling curve will be a mirror image of the heating curve. Now let's start with effects of impurities. So effects of impurities on melting point and boiling point. Let's first discuss melting point. So impurity lowers melting point. Impurity lowers melting point. Now why is that so? Because just assume that there are two friends, they have a lot in common and they have a very good friendship, and suddenly a third friend comes in, and the friendship between the original two friends decreases. It's a little silly example, but you I think you might get the point. So impurity causes a lowering, or impurity causes the lowering of the van der Waals or the intermolecular forces of attraction. Impurity. So the reason is impurity weakens the intermolecular force of attraction. Now, what does this mean? This causes that less heat to be required for the substance to melt. I'm sorry for the noises behind. It's just the fireworks because of the New Year's Eve. By the way, Happy New Year's to all of you. Alright. So, one more thing. For example, just give it a thought. Will sugar be a better impurity or salt? So, the answer is salt. Now, I'll tell you the reason. When I dissolve C6H12O6, what is known as sugar, in water, it will just remain 1 mole of sugar, C6H12O6. It will become aqueous. Alright, just 1 mole. But for example, if I add salt in water, I get 2 moles of impurities, 2 moles of ions. So generally, ionic compounds are better impurities than covalent compounds. And by the same logic, strong acids are better impurities than weak acids. If you do not know why, don't bother, because I'll be teaching it in acids, bases and salts chapter again, so you do not need to worry. Strong acids are better impurities than weak acids. Alright. Now, one more point. The more the impurity, the lower the melting point. The more the impurity, the lower the melting point. The lower the melting point. Right, now let's get to boiling point. So impurities higher the boiling point. Impurities higher the boiling point. Now why is that so? So as I was talking about earlier about boiling, I told you something about vapor pressure. Now what impurity does is, for example, this is an impurity particle, and this is a water molecule trying to escape. So it starts to rise with the energy enough to just escape water and break the intermolecular force attraction. However, these impurity particles come in its way. Now what happens is the energy of the vapor or the water molecules decreases. So what happens is eventually that impurity lowers the vapor pressure. Now more heat will be required to produce the same amount of vapor pressure to overcome the atmospheric pressure. So that causes more to be required. So one more thing is that impure substances melt and boil over a range of temperatures. Now I want you guys to pause the video and try to make the heating curve of impure ice. So okay, I hope that you have done it. Now let's see how I have done. Alright, so let's see. So for example, this is I take ice at minus 10 degrees Celsius and I start to heat it up. It reaches 0 degrees Celsius. But now what happens is it starts to melt, but as it melts over a range of temperatures at below the melting point, so the curve will look like this. You see, it's a range of temperature. For example, it's minus 4 random value, let's say, and this is 0. So it melts at a range of temperature, and when all of the ice has melted, the temperature rises until it reaches 100 degrees Celsius. Now again, it boils over a range of temperatures above the boiling point. The graph will look something like this. Let's say this is 104 degrees Celsius, and then it starts to increase again, right? So this is a heating curve of an impure substance. Now most of our chapter is done. In fact, all of the chapter is done. States of matter is now complete. I hope you enjoyed this, and happy new year's to all of you. Goodbye.